Hello everyone. Today I'm going to talk about our paper, Sensor Localization by Field Distance Measurements via the intersection of implicit manifolds. Algorithms like SLAM use a range of distance measurements in order to localize a robot. One question that arises is whether we can only use a few distance measurements to determine the pose of a robot. Furthermore, perhaps we can use this as an insight and get an algorithm for robot localization where the robot moves and rotates in space, measures the distance, and uses this to get a close approximation of its true pose. Formally, assume we are working in a planar workspace. Given a set of rigid body transformations, which might be the transformations the robot performs in space, or perhaps the offsets of multiple distance sensors mounted on top of the robot that stays still, and a corresponding set of distance measurements. We strive to find all poses for which, after translating accordingly and measuring the distance, we get the corresponding distance measurement. Our key for solving this problem is going to be the approximation of preimages. Given a distance measurement, its preimage is defined as a set of all poses for which, after performing the corresponding transformation, we measure the corresponding distance. Our method is going to be as follows. For each pair of distance measurement and a rigid body transformation, we compute a voxel approximation of the preimage. Then, we intersect the resulting voxel approximations, and, assuming we performed at least 3 measurements, we can use that intersection to extract pose estimations. The first step is going to be the voxel approximation of preimages. We use a simplified version of the marching cubes algorithm. For each voxel in an n-cubed grid, where n is a parameter controlling the resolution of the grid, we evaluate the distance measurement for each vertex of the voxel and report the voxel if we have 2 vertices, one that measures the distance that is larger than the target distance and one that is less. The second step is overlaying the grids of each preimage on top of each other and keeping only the common voxels, hence intersecting the voxel approximations. Finally, if we have performed at least 3 distance measurements, our intersection is going to be a union of dot-like clusters, from which we can get the center of mass, apply some light filtering and heuristics to get rid of outliers, and extract pose estimations for the robot. We also prove guarantees for our method. Our true pose is contained in its voxel approximation, and our error is 1 over the grid resolution, hence, the error is lower the larger the grid we take. We are also robust to bounded measurement errors. These results are true up to some blind spots, which are voxels that we need to deal with separately. We have an exact computation that achieves those guarantees, but we also implement a simpler heuristic which achieves 100% success rate in practice. We implemented our method and performed the following experiment. We placed the robot in random poses in different polygonal rooms, transformed the robot randomly, and measured the distance. Then, we applied our algorithm and compared the distance between the ground truth pose and our closest prediction. As we can see, this error is indeed small and decreases for larger grid resolutions. We also get a promised 100% success rate, in the sense that the ground truth is indeed one of our pose estimates, and we also suggest a heuristic for choosing one pose estimate out of the set, which has high success rate. Our algorithm works well even on old, slow hardware and is scalable for GPUs and other multi-core hardware. Finally, we performed physical experiments with a robot, which we placed in various rooms, equipped with a single distance sensor. The robot performed 6 measurements, with increments of 45 degrees, and indeed achieves relatively low error in both position and rotation. Even though our algorithm works in real life, in the future we would like to further improve the accuracy and success rate of this method. We would also like to deal with perhaps unbounded stochastic errors, choose an optimal intermediate motion instead of a predetermined one, and extend our method to higher dimensions. Thank you for joining us.